Hello and welcome everyone. In this day 26 learning of binary tree problems, we have covered uh, tree introduction and different properties that come along with the tree, and we have also looked at different tree traversal techniques like post order or in order or a pre-order traversal techniques. Now now let's take some binary tree problems and let's try solving them. So I have pasted some number 15 number of problems here, which would be like an interview type questions, and I we are going to try solving few of them, and the other should be very relevant to the ones that we solve. So just follow this video and try solving them. Please do post your thoughts or any questions in the comment section. We shall solve the problems if you find anything difficult, right? Let's get started. So first problem would be find the maximum value in a binary tree. Given a root of binary tree, not necessarily a binary search tree, traverse the tree and return the largest integer value stored in any of its nodes, right? So let's say we know that binary tree has two a specific node would have two nodes. Let me switch to JS bin. Yeah, so here binary tree. So I have created a simple tree node which takes in a value and left and right pointer, which initially if we do not assign anything, it takes up null values. So we want to find maximum value in a binary tree, and we need to return the value maximum in this specific binary tree. And let's say we have this set of driver code. Maybe if you see here, I've created uh, two binary trees, one with 3 and one with 5, right? So we have created it this way, and this one is having a root node of 50 and 30 and 100 and 10 and 40, right? So find maximum within this specific binary tree, which is 5. Similarly here, this is 120, right? So find max is the function. So we need to implement this function. So we can think about this. Maybe let's go back to our drawing board. Let's start thinking through this, how we can uh, design such a solution, right? So I will open a new sheet. So find max, and yeah, so 315, and another example was 50, 30, 100 and 10 and 40, 80, 120, right? So these were the two set of things. Okay, so we need to design this find max function, which takes in a node, and let's say it returns a maximum value. So let's take this simple example for now. So uh, we know that this is a simple binary tree which consists of one root node and two nodes, that is left and right node. So here we can simply draw out saying the current node and left node and right node. The maximum value out of these should give us the maximum value. Let's say once we come down to such a problem which has n number of levels or children's, We should also know that these two will be pointing to null, right? As per our tree node implementation, all of these also will have null at the last order, at the last level, right? So if a specific node is equal to null, then we can simply return minus infinity. And let's say if there is some number of uh, left binary tree portion, then we can further ask this max function to work as a recursive function to give us left max, which is equals to find max of node dot left. Similarly, right, we can also send in the right portion of it. That would give us left max, which is part of this one, and and right max. This way we can build this recursive function to uh, fetches the maximum value out of this binary tree or any level of binary tree, right? So the way that this recursive function works is, so we start at node 3 and we take left portion, which is 1 and 5. We calculate the maximum out of these three, right? This is the max and we return this. In case of this one, which is example 2, in case of example 2, where we have 50, which asks for left max, which again goes with the current node 30, and it has a child node of 10 and 40. This will return 40. In case of right max, it will go fetch 100 and 80 and 120, right? This will be 120. So finally, 50 left max and right max. Left max is 40, right max is 120. This will lead to, this final expression will lead to 120. So this is the final solution that we get. So let's switch back to JSPin editor and let's see how this runs, right? So let me quickly run this code. As you can see, for the first binary tree, which is DLA, 5 is the result, which is the maximum value, and DLB, which is the second binary tree, we get 120 as the maximum, right? Try playing around with this, and let's go to the next problem. Please do uh, understand the recursion, which is the most important topic to solve many different binary tree problems, right? So let's go to the next problem. Okay, let's go back to the questions page where we had questions. Yeah. So search for a value in binary tree. Implement a function that gives the implement a function given the root of a binary tree and a target value. Return true if a node contains the value and false otherwise. Okay. So I will quickly share the solution. Maybe you can quickly see how it runs. I will also paste in the detailed solution in the GitHub link, which contains all the problem statements and the solutions to them. So you can go through them at if you do not understand any, or if you do not find any if you do not find a good solution for a problem statement, right? Use that as a reference point. But please do try uh, solving it yourself, right? Let's switch to the JSPin editor. So here I have a function which is defined as contains value. We are going to pass in arguments such as root and target, and we are going to find if a specific binary tree has a target value, right? So let's say we have created this binary tree here, and we are searching for values such as 5 and 7 and 0, where 7 doesn't exist and 0 and 5 exist, so we return true, right? So how we are going to do this is, first thing is, let's consider a simple binary tree, let's say this portion of it, and we check for uh, uh, we we are checking for the left and right target values. Let's say first thing is we check if the current root node value is equals to target, then we simply return true. Else we also drill down to the left and right portions, checking if uh, they still have a value with recursive function call as we see here. And if none of the roots, and if we reach the end without any match, then we simply return false, and that trickles back all the way up. Let's say in case of 7, we go all the way to each and every node, we see a 7 not existing, and we return false, right? So this should also be similar to the one that we saw previously. It's just about recursion being implemented here, right? Okay, let's go to another problem. Okay, so insert a node in level order. Insert a new node with a given value into a binary tree at the first available position found during a level order traversal. Tree should remain complete as possible. Return the possible unchanged root. Okay, so yeah, let's switch to JSPin and let's try solving this problem. Okay, so here I've added another helper function which helps us to print a specific binary tree in level by level, right? So coming to the problem statement, we are going to insert a binary tree element into a binary tree in first available position. So this is the specific solution for it. So let's consider this specific example: 1 2 3 4 5. So there are no nodes for this element 3, that is, there is no left and right nodes. So what we need to do is we need to identify a specific node that doesn't have any left or right nodes, and then start adding them, or we can create a new uh, node after this specific 4 or so, right? So that's the whole idea. Okay, so let's see how it is done. So to find the spot, we are going to firstly push the root element to the queue, and we are going to explore the left path and right path. If there is no node in the left path, then we immediately push the new node that we want to uh, insert by creating a tree node out of this value. And similarly, if there is no node in the right, then we push it to the right side. Else we push them to the queue to start further exploration of the left and right portion of it, right? So that's the whole idea. So so I have even added another node to insert. If you see, I have added another three insert statements here. One is 6, 7 and 8. 6 and 7 can go under the node 3, while this new node will take up a next level, uh, that is the fourth level, right? So that's the whole idea. And I've even added this helper function to print such log messages which show uh, the level by level tree structure. 1, 2, and 3, 4, 5, and 6. 2 contains 4 and 5. 3 contains 6 and 7. And 4 would contain 8, which is the rightmost node. Okay, so hope you understood this problem. Let's go to the next problem. So the next one is again a pretty easy problem. Compute the size of a binary tree. Binary tree. So return return the total number of nodes in the binary tree, right? So let's quickly look at solving this problem. This should be an easy one. I've already pasted the solution and we have already utilized size of a tree function here, if you already identify. So if there is no root value, then we return 0, else we keep adding 1 to the size of it, right? So that's the whole idea. So let's say we calculate all the different nodes in this binary tree, 1, 2, 3, 4. So we add 1 to it, right? So that's the whole idea. Hope you understood this quick. It should be a recursive kind of an implementation, and it should be very much easy to uh, build it up if you are following all these 3 examples that we have solved previously. Okay, let's switch to next problem. Next one is delete a node while maintaining the tree shape, right? Similar to insert, we are going to look at delete a node while maintaining the tree shape. Okay, so let's start understanding this problem. Delete a node from binary tree. Delete the first node found with a given value. For general binary tree deletion, to maintain shape, replace the target node's value with the deepest rightmost node's value and remove the deepest node. Okay, so let's understand this problem. Maybe I will switch to the drawing board and let's draw this out for better understanding. So let's say we have a simple node 1, 2, 3, 4, 5. So we are required to remove target node and replace rightmost node, rightmost deepest node. So let's say we want to remove this, we would replace this with the 5. This is the rightmost deepest node, or this would be the last value that we are going to see in this binary tree. So what would happen is 1, 4, and this would be 5, and this would be 3. And let's take another example. Let's say we have something like 50, 30, 100, 10, 40, 80, 120. So let's say we want to remove 30. The rightmost value that we would be inserting here is 120. So this would translate to 50, 120, 100, 80, and 40, and 10. So this is how it's going to look like, right? Hope that makes a little more clear. Let's switch back to the problem statement and let's understand the problem. So the implementation is here we are going to check if there is no root, then we return null, and if there is a single root without any nodes, then we are simply going to a single node with no left or right values, then we are going to check if that matches the value that we are looking for, and we simply return the root, right? So else we start tracking the target node that we want to find, the first finding as we iterate through the binary tree, and the deepest node that is the rightmost node, right? So we update the deepest node and also the target node in such a way, this way, by BFS traversal in this while loop. Once we have a target node, we do these set of operations, else we simply return the root node. Once we have a target node, we replace it with the deepest node value, and we remove the deepest node also, right? So yeah, so the deepest node wherever we find, we also change the values of uh, the specific node, the deepest node value to null, and we simply return the root node after all this operation. So just to understand, so here we have some driver code with example. Let's say we have size of a tree before deletion is 5 for this one. We start deleting the node 2. We move this rightmost node, which is to this position, which gets 5 and 3, and this stays here. Now let's say we try to remove 99. There won't be any deletions as we won't find any target node, and hence we simply return the same root node. Next, if we try to remove the root node itself, then we end up with 4, which is the deepest node, and we get 5 and 3 as the children node. So this was about insertion and deletion of a node in binary tree. Hope this was meaningful. The next set of problem statements are with respect to height of a binary tree, which should be easy again. Follows a simple recursion. We check if there is a root value, else we return 0, else we add 1 and we traverse to the left and right portion of it, and we return the maximum height of the binary tree, either left or the right? Next thing is we need to find depth of a node, distance from root, right? So let's say we are given with this specific node for 6, we see that there is depth of 3, right? So we increase the depth which with each recursion, either left or right. So we have a queue which stores an object of node and a depth value as a pointer to keep track of the depth of the node, right? So this should also be pretty much easy to understand. Please go through these examples, right? Print all leaf nodes. I think we have even tried some this similar example in the day one learning of trees intro and properties in couple of days ago. Yeah, so that's one thing to also note, right? So it was in day 24 learning, right? Hope you could remember this. So in a small variation of this, we are also having to track half nodes with exactly one child. Like let's take this example where 3 has only one child, 6. Similarly 5 has 7, right? So those are the two nodes that we are returning. Okay, so one last problem that I would like to go through is, so far let me node list, identify half nodes. Yeah, one last problem that I want you to take an attempt or see how you can solve this problem, and please do let me know the solution or different ways of solving this. Maybe please do keep the comment section active, and this is an opportunity for me to also see the different ways of solving this maximum level with maximum sum, right? Take this problem statement and please do communicate if you have different solutions or any creative solutions for this problem, right? So level with maximum sum. Okay. So we need to find binary tree where there is a level, uh, in a specific level, all the nodes needs to be summed up, and whichever level has the maximum sum, that needs to be written, right? So that's the whole idea. So let me just share my initial solutions for these two problems here. Okay, so let me run this solution where we have a solution for maximum sum level. So here we are checking if there is no root, we simply return level is -1, and we simply also return the sum of it, and we are keeping track of the level and also the best sum that we are going to find at a specific level, right? So this is the whole code. uh, this should be pretty much easy to understand, where we are checking all the size of nodes at a specific level, and we are calculating the sum at this specific sum, and also we are even pushing the next set of nodes in the next level, that is the nodes left and right to a specific node at a level, and then we are even checking if the level sum is greater than the best sum, then we swap the values and also add in the new level sum and the specific level, and we increase the level, and we continue till we complete all the breadth for BFS or level order traversal. So that's the whole idea. So for example, here we have in this specific node, we have this as the level 3 would be uh, level 3, level 2. Level 2 would be the highest sum. In case of this one, level 1, which is the highest sum. In case of this one, level 1 is the highest sum, right? That's very clear looking at the problem statement. Let's we would not be touching on these other problems, it can be easy to understand, but one last problem that I want to go through is having to construct a binary tree from in order or level order traversal, right? So yeah, let's understand binary tree construction problem. Okay, so the base case here is or few basic conditions to this function is, we take an in order array and level order array, and we check if both of their lengths are existing, and if their lengths are matching, else we return null, and we start this recursive function, which all we are doing is we should know that these two arrays, which are part of this binary tree construction 1 2 3 4 5, we need to know that in order would be 4 2 5 1 3, right? So level order would be 1 2 3 1 2 3 4 5, right? So level order would be based on the different levels, and in order would be uh, left and the right and the root node. That's how it is. And the whole idea here in construction of this binary tree given an in order and level order traversal is, first thing is we we see which is the root node, taking level order as a reference. The first node would be the level order node, and then we populate the left values and the right values, right? So these are the left set of nodes and the right set of nodes. Once we have the left and right nodes, then we iteratively start uh, going deeper, saying that 2 is another root node, and then we start building left and right nodes for these two. That way we populate a binary tree, and this would be the implementation for it, right? Just go through this example. This would be the most complex one, but other tree constructions would be something similar, but yeah, you can get the idea, right? I would stop this video for now. Please do uh, write any comments or any sorts of doubts or any sorts of discussion points that you want to have with me. Hope you found this video helpful. Please do like and subscribe to my channel. Thank you.